Hey there folks, welcome back to the program. I'm your host, a disembodied voice with a New York accent. This one's going to go over the approach I use to set the sizing and geometry of a bike board. We are here in the glorious expanse of cyberspace because we're not really going to be building anything. Today is just about theory. And yes, there will be a test after the video. So, first things first, we need to accommodate the rider. I'm drawing the size of the deck based on how wide this guy's feet are and what kind of a stance he wants to hold while riding. The next major component is the wheels. As you can see, the size of the wheel determines how short you're going to be able to make the wheelbase before the wheel collides with the deck. Oh my god, this is just like the Mona Lisa. So if we keep the ride height and the clearance between the wheel and the deck the same, you can see there's a trade-off between the size of the bumps you're able to handle versus the standing platform and the wheelbase. In comparison, the size of the tire plays a much more important role, which you can see when viewing the vehicle head-on. This angle I'm drawing right now represents the maximum lean angle the board can hold before the deck hits the ground, with a steeper line meaning a steeper lean angle. And as you can see, if we keep the ride height the same, a smaller tire will permit a smaller amount of lean angle than a wider tire will. In this case, the difference is about 5 degrees. The size of the tire also affects how much you're able to steer the board before your ankles give out. Imagine you're trying to make a tight turn at low speed, so your body isn't leaning very much, but the board is. According to your ankles, you're not going to feel the board rotating around the contact patch on the ground, but around the center of the tires. If you lean the board over so that either the ball of your foot or your heel goes past this vertical line, which represents your center of mass in this situation, you won't be able to support the board anymore, and it'll just tip all the way over. A larger diameter tire will let you lean over further before your heel or your toes goes past the tipping point. In this case, about 5 more degrees. So, adjusting the ride height controls the trade-off between tip-over angle and lean angle, but a larger diameter tire lets you get more of both.
But enough computer programs, let's do things the civilized way and use CAD. Now, bike boards will work just fine using a conventional bicycle steerer tube and fork, but it looks kind of dorky and tried and true methods are for suckers anyway, so let's talk about 4-bar linkages. The steering mechanism has one link running parallel to the axle, which I'm labeling A. It's got 2 following links, which I'm labeling B. And it's got a ground link, which I'm labeling C. In linkage lingo, the ground link is the one that you consider to be stationary, and you measure the rotation of the other links relative to. For our purposes, it's the deck. Also, it's worth noting that each of these links can do all sorts of wavy, wibbly-wobbly stuff between the pivot points. For kinematic purposes, all we care about is the distance between the pivot points. Unlike a conventional steering mechanism, a 4-bar linkage does not have a single axis of rotation. The point that it rotates around at any given instant depends on the intersection point between the 2 following linkages. So, this mechanism could be rotating around this point right here, or anything in between. That gives us the information to determine how much trail the mechanism has, which I'm defining to be the distance between the instant center at 0 steering angle and the contact patch of the wheel, represented by this string. A rolling tire that's not being acted on by a drive system or brakes will always produce forces parallel to the axle, which is represented by the fact here that I'm always pulling on this string parallel to the A link. Unlike a conventional steering system, a 4-bar mechanism will eventually reach a point where this line of action passes through the instant center, and the mechanism will stop steering. Obviously, we're interested in maximizing the angle that we're able to steer, but how do we do that? Trail is easy to figure out. Here you can see that I've set it up to have less trail, and clearly the lockout angle is smaller now. But figuring out what these other 3 parameters do is a little more tricky, so I'm going to have a computer solve the problem for me instead. In order to organize the data in the computer a little more clearly, I'm going to be describing the dimensions of these mechanisms using a length and a width ratio, where the width ratio is c divided by a, and the length ratio is the forward distance from the ground link to the axle link, again divided by a.
In order to do that, I've loaded up the program Octave, which is like open source MATLAB. In broad strokes, what it's doing is to calculate the position of the instant center and the force vector coming from the contact patch, and then using the secant method to zero in on the steering angle that makes that torque go down to 0. Then, once it's found the steering angle, repeat that for a whole bunch of different width ratios, and then length ratios, and then draw a pretty graph of the results. If you want to mess around with this program yourself, I will be leaving a link to the files down in the doobly-doo, and then once you get it loaded up, the only real thing you're going to want to edit is the amount of trail you're using, the range of length ratios that you're going to use, and the resolution at which you're sampling that, and same for the width ratios. Just hit the run button and it'll get to work. In a while, depending on how high your resolution is set. So I've gone ahead and generated 30 graphs from 30 different trail values and compiled them into this video file for your viewing pleasure. Again, the link is going to be down in the doobly-doo. So what does this tell us? You can increase the length ratio of the mechanism, but you get diminishing returns from that. Likewise, there's diminishing returns from increasing the width ratio. There seems to be some optimal combination of the two somewhere in this region here. And as you move up this region towards the top right corner of the graph, the steering angle gets better and better. Now, because I'm defining both of these dimensions as a ratio to the length of link A, moving upwards along this diagonal can also be interpreted as just decreasing link A. It appears that that's really the most important factor in designing this. You want link A to be as small as possible. But of course you get diminishing returns from that too. As you can see towards the top right of this graph, the topological contours are approaching that 45-degree diagonal, so it doesn't appear like it's going to end up going much over 50 degrees. Or hell, I don't know, maybe it can. But my script appeared to be breaking down a little bit in this region at the higher steering angles. Now let's take a trip to the third dimension of this graph and see what effect the trail has. As we can see, at large trail values, the geometry of the links becomes less important. You get a large steering value pretty much anywhere in the design space, because the trail is the driving force. At small trail values, the geometry of the links is much more important. As you can see, there's only a small region of the graph where you get a decently large steering angle. So it sounds like more trail is good. It's going to let you pull off a tighter turn at low speeds, perhaps. But there is a catch.
More trail will give you more leverage to steer the front wheel, but when the board is leaned over, steering the front wheel will move the deck away from and towards the ground. And of course this effect will be larger the more trail you have. So a board with a lot of trail is going to need some extra ride height at the front of the deck in order to maintain the desired amount of lean clearance in turns.
Now let's go back to SketchUp to draw the geometry of the mechanism and see how it fits into the board. I'll start off by making the total width the same as that of the deck, taking a random guess for the length, connecting those to form the following links. Now let's just take a random guess and say that I want to have the axle link be 150 millimeters. I'll just drop that into place right there. As I've mentioned before, the trail point is where the two following links converge, so I've dropped a perpendicular line there just for reference. Now let's say I want 100 millimeters of trail. I'll extend that line out from the bottom point of the wheel. Now I can take my mechanism and just drag it over there. And as long as this perpendicular reference line passes through that point 100 millimeters in front of the contact patch, the mechanism will have 100 millimeters of trail. So every rotation or transformation I do to the mechanism over here has to be with respect to this point. For example, say that I want to have 15 degrees of rake, I can grab the mechanism around this point and tilt it over by that amount. You can take any of the pivot points and translate them up and down along the steering axis like this, and it won't actually change the behavior of the mechanism. The only thing that matters is how the mechanism appears from this perspective, normal to the plane of the linkage. And changing those positions doesn't really do that. So now I'll just double check what I've got here. I've got 96 millimeters of trail measured normal to the steering axis, 150 millimeter axle link, 363 millimeter ground link, and a length of 176. That works out to a trail ratio of 0.65, a width ratio of 2.4, and a length ratio of 1.2. So if we look that up on the chart, it comes out right here. We can see that we're going to get about 31 degrees of steering, which is serviceable, I guess, but it's not too great. Since I started off the drawing with something that was pretty close to an equilateral triangle, the mechanism is in that sweet spot where changing the length or the width by itself won't do much. I have to decrease the length of the axle link. So I'm going to do that by redrawing that line, and I'll draw the axle link to be 100 millimeters instead of 150. This version of the mechanism has a trail ratio of 1, a width ratio of 3.6, and a length ratio of 1.8. Going back to the chart, that puts us right here at about 40 degrees of steering. Here's the model of my own project to show you how I approached the problem. It looks a lot more visually cluttered, but don't worry, the familiar 4 bars are just hiding right here. I made the axle link as short as I could, that's about 74. We've got a width of 381 and a length of 222, all with a trail of 100, which comes out to a trail ratio of 1.4, a width ratio of 5.1, and a length ratio of 3. Referring back to the chart, we can see that I did not have the foresight to make the chart large enough. Oh well, it'll steer around like 45 degrees or something like that. Looking back at the model, it unfortunately would not have been possible to achieve that if the axle link was next to the wheel, because I'm using a pretty wide wheel for other handling purposes. Because of that, I've just translated the forward pivot points up above the wheel and used about 25 degrees of rake to make sure that I get the trail point correct down here. And that's it for now. The next installments will be about fabrication techniques to build this thing. I hope I've been clear enough, but if you've got any questions, leave them down for me below. Thanks for watching.